Okay, what's one thing that is a stress? One thing that is a stress, Keita. Come on, we did like anything that's a stress. What could we do to a system to stress it? Heat or something. What do we call it? Temperature. We could change the temperature. See, you did know something. There you go. Not here. What's another stress? Kia. Concentration, a change in concentration. And Zoe, what's another stress? Pressure, volume. Okay, so now we're moving on to things which are not stresses. And so the things that are not stresses are, number one, catalysts. Number two, liquids and solids. And number three, inert gases. Liquids and solids, because liquids and solids don't ever change in concentration. Okay? The effect of a catalyst. Now, if you recall, how does a catalyst work? Tell your partner. How does a catalyst work? Okay, so a catalyst provides an alternate pathway with a lower activation energy for both the forward and reverse reactions. And it speeds up both rates the same amount. Okay? It provides an alternate pathway. So if this was our...
No, I said like, why it's not the stress.
It's not a stress because it provides a lower activation energy for both the forward and the reverse.
It doesn't provide like the speed to particles itself. Like it doesn't do.
It does not provide any speed to the particles.
Exactly.
Okay?
And it's not the stress.
No. Okay? The catalyst does not change the speed of the particles.
Neither does that provide heat.
It speeds up both rates the same amount, and if both rates are still equal, then we are still at equilibrium, and there's no shift. Okay? Do you guys think you could try drawing a rate diagram and a concentration diagram for this one? We've just got A going to B. Okay? Give it a try. Should be getting good at these diagrams by now.
Since there's no stress, it's literally just a straight line.
Your wig looks so great.
What?
It does. Yeah.
It stays like no, it speeds up. So like it's like it's not shoot, just goes up. It's like
Of course, you can't compete with Matthew over here. Matthew's got the ultimate wig. How can you argue with a mullet? Come on. Once you've got your graph drawn, show it to your neighbor, see if they got the same thing as you.
You want to risk it? We can always erase it.
Okay. What happens to our forward rate?
It goes up.
Yeah, when we add a catalyst, when we add a cat, forward rate goes up.
Oh, straight up. But
I don't know.
no, it's not straight up.
No?
No, yeah, it just speeds up. It's all straight up. I thought it was just like a curve, like steep shallow.
Anything that we do to a system is a spike.
Oh.
Anything we do happens instantaneously. Anything we do is an instantaneous change. What happens to our reverse rate? It also goes up. Does it go up by less than, more than, or the same? The same. So it should end up at the same place.
Wait, if it's a spike, then it shouldn't be a stress.
No. We do what's what we do to the system. So stresses are all what we do to the system. This also happens to be what we do to the system. Okay? And now there's nothing that they can do but just do what? They would go, shoo, but how much shooing is there if they're right beside each other? No shoe, just no shoe. Okay.
But with this, it doesn't go back down.
It does not go back down, not like it just stays higher because now you've got a lower energy pathway, right? All right, now our concentration diagram. What happens to our concentration of A and our concentration of B? Nothing. I'm going to draw it in a different color just so you can see where the change happened, but really absolutely nothing. Okay, when we add a catalyst, nothing, because we're still making and the rates of the reaction are still equal. All right. We are now going to draw a rate diagram starting with reactants only. And we're going to do it with and without a catalyst. Okay? Are we? Or am I just going to go to the next page? No, we're just going to go to the next page because actually I find this really irritating to draw and I can't really draw it. So we're just going to go to the next page. Here is a picture of what happens with a rate diagram without a catalyst is this one here. This is starting with reactants only. Okay? So we're not at equilibrium to start. So if we're starting with reactants only, the rate starts fast, forward rate is fast, and the reverse rate is 0. Yes? And then we come to equilibrium. That we looked at that at the very beginning of the equilibrium section, right? When we just started with reactants. Now, if we have a catalyst, and the catalyst is in there from the very start, What's going to happen to our forward rate compared to what it was without the catalyst? It's going to be higher. So this is our forward with catalyst is faster. And the reverse rate still starts at 0. But when do they come to equilibrium? Way sooner. So with the catalyst, the system reaches equilibrium sooner. Without the catalyst, the system reaches equilibrium later. You guys are okay with WO being without? And the overall back and forth rate is faster with a catalyst because you've just got that lower activation pathway. Okay, so the moral of this story, you're probably not going to have to draw this, but the moral of this story is that you reach equilibrium faster with a catalyst than without a catalyst. Yes? Quick review, concentration diagrams, where we are starting with reactants only. And remember now, these are concentration diagrams, not rate. The two that were above, those were rate diagrams. These are concentration diagrams. We might have a situation like graph A, where at equilibrium, what can we say about the concentration of products and the concentration of reactants?
Products are higher than reactants.
Yeah, the concentration of products is greater than the concentration of reactants. In B, what can we say about those two concentrations? Concentration of reactants is greater than, yes, concentration of products. So these might be two different reactions, or it might be just the same reaction at different conditions, maybe different temperature, maybe different pressure, something like that. In diagram A, the position of the equilibrium sits more towards the products. And I don't remember if you remember the language around that, but we can say that the system favors the products. And actually, while we're here, I'm going to introduce the concept of KEQ. KEQ is the equilibrium constant. Don't worry. This is just a brief intro, so you've heard the term and you've seen it before. We'll come to a whole section on it later. The equilibrium constant. So here, KEQ is always equal to the products over reactants. And in this case, the concentration of the products is big, and the concentration of the reactants is small. And if that is the case, what can you say about the value of KEQ? It's going to be not necessarily a whole number, but it will be larger than what? If the big number is bigger than the little number, that will be bigger than 1, okay? So I thought that's what you meant. Okay, so in this case, KEQ is greater than 1. So in diagram A, the system sits more towards the products, it favors the products, and KEQ is greater than 1. For diagram B, KEQ, which is still equal to the concentration of the products, but this time the concentration of the products is small. So I'm going to draw it little. Concentration of the products is small. Concentration of reactants is big. And if that's the case, what can we say about the numerical value? It's going to be smaller than 1. Yeah. So in diagram B, the position of the equilibrium sits more towards the reactants. And we can say the system favors the reactants. Okay. The effect of an inert gas on an equilibrium position. Adding an inert gas, what does the word inert mean?
Or non-reactive.
Unreactive or non-reactive. In other words, the which gases? The noble gases. To an equilibrium, does that affect the concentration of the reactants? No. So it does not affect the concentration of the reactant molecules. If it does not affect the concentration of the reactant molecules, or the product molecules for that matter, does it affect the rates?
Yeah.
The rates are not effective because we've not changed the concentrations and we have not changed the temperature, okay? The only reason why volume causes a stress is because it changes all of the concentrations of the gases, okay? Rates of forward and reverse reactions are not affected, therefore adding an inert gas causes no shift. Sometimes people get weirded out and they're like, oh my gosh, sometimes the helium's going to get in the way, it's going to slow it down, or they're like, it's bouncing off helium and so it bounces into particles more. The answer is no. For every little real reactant collision that's blocked by a helium, another one is caused by a helium. It works out randomly that way. It looks like helium's going to have a big effect on the particles, but in reality, how close should we be drawing these particles to one another? Not very close. They look really close because I wanted to fit it on the side of this page. Really, we should have a diagram that's like this big, and we'd be like, here's my reactant particles. And then we throw in a couple heliums. Yes? And it really makes no difference whatsoever. Okay? The overall pressure changes, but the partial pressure, the pressure due to the hydrogen and the pressure due to the nitrogen here in this example and due to ammonia would not change. So the concentrations are not changing. Okay? You do not need to explain why an inert gas does not cause a change. You should just know that it does have no effect. So, could you please draw a rate diagram and a concentration diagram for when you add an inert gas?
this one's gonna be straight.
Yeah, this concentration.
What about the rate? The rate is also.
Oh, yeah.
Right? Okay, what happens in our rate diagram? You guys are still drawing. I'll wait. When you're done, check with your partner. We'll check on you.
Do you have any ways of memorizing like the thing faster? Not the like just explain it in terms of rate and explain it.
I would just think about it. I'd be like, what happened to my rate? Why did it happen? That's the fastest way, is to really understand it. And then you don't have to memorize it. And in order to do that, I would make my own study notes about it, probably. Okay, what happens in our rate diagram? Nothing. What happens in our concentration diagram? Nothing. Are we good with that?
This is the best unit ever.
Right? We like this one. Inert gas, just straight lines. Okay, let's look at changing the amount of liquid or solid. The easy way to think about this is that liquids and solids, they are pure substances. Pure substances do not have concentrations, okay? Or at least not meaningful concentrations. You cannot change a concentration. Also, concentration is like moles of solute per liter of solution. So it means there needs to be a mixture. Yes? So anyway, something to think about there. Therefore, changing the amount of solid or liquid in an equilibrium system will cause no shift. So you can just be like solids and liquids, no shift, good to go. Okay? I can change the amount of liquid, I can change the amount of solid, no difference. Here is a solubility equilibrium. This is a low solubility salt, which means that it will, some of it will dissolve, but only a very small amount, okay? And then what will happen is that for every particle that dissolves, once it's saturated, for every particle that dissolves, another one will recrystallize, okay? So here we have an ionic crystal lattice, and it dissociates in water. All right, and we keep adding more. So we add some, and we add some more. And eventually, no more solute dissolves. The solution is now saturated. That's what it means to be saturated. You cannot dissolve any more. So any more that I add now stays as solid. There is a limit to the concentration of ions in a solution. Once a solution is saturated, for every 1 mx, which is like the metal and the nonmetal that dissolves, you'll get 1 m and 1 x minus recrystallizing.
Oh, so it's literally like just do nothing.
It's literally doing nothing. This is an equilibrium because the rate of dissolving equals the rate of recrystallization. So our equilibrium system would be mx in equilibrium with, sorry, this should say solid, m plus aqueous plus x minus aqueous. No.
Oh,
Okay? But I'm just saying this is our equilibrium system. Yes? The rates are equal. Dissolving equals recrystallizing. Now, if you have a small pile of solid, like you do here, all right, the rate of dissolving will be fairly slow. So the rate of dissolving, fairly slow, because there's not much surface where dissolving can occur. So maybe you have these two particles, they come off and they form m plus and x minus. But anytime that happens, what's going to happen over here? M is going to recrystallize, okay, and X is going to come along and recrystallize. So the rate of recrystallizing is, again, fairly slow because of the low surface area. So these rates are slow but equal. Slow and equal. So this is a saturated solution. Saturated. So now let's say that we add more salt. Yes? Even though it's saturated, we're going to dump in more of the solid. All right? So now we've got all of this is solid down here. Still saturated. We have more solid. Now we can have M and X coming out and another M and X coming down. We can have M and X coming up and another M and X coming down. There's a lot of surface at which recrystallizing and dissolving can take place. So what has happened to our forward rate? The forward rate has increased. The reverse rate has increased. The reverse rate increased. But did they increase by different amounts or by the same amount? So these two rates increased by the same amount. So are we not at equilibrium or are we at equilibrium? We're still at equilibrium. It's just like the case where we had the catalyst that sped up both rates equally. Okay? So we're still at equilibrium, but it's just that the equilibrium is faster. And I didn't have you draw a diagram for this one because it would look exactly the same as the catalyst diagrams. Okay, the diagrams are just like the catalyst diagrams. So those are things that are not stresses. So making quick predictions. I mean, honestly, I think you guys have gotten pretty good at making quick predictions just based on the fact that, you know, we've been doing a lot of these. But just in case, if you have a concentration increase, the system shifts away from the increase. If you have a concentration decrease, it shifts towards the decrease. If you have a temperature increase, it shifts away from the heat term. If you have a temperature decrease, it shifts towards the heat term. If you have a volume increase, it shifts to the side with the larger total amount of gaseous entities. Can you tell I copied this from somewhere? Gas molecules. Gaseous entities just means gas molecules. And if you have a volume decrease, it shifts to the side with the smaller amount of gas molecules. Catalysts, no effect. Inert gases, no effect. We could add solids and liquids. No effect. So you have a quick reference chart, and now we're going to do some quick practice so you don't have to think. Yeah? Because it's all very well and good to be like, yes, it's shifting this way, and this is why, and this is shifting this way, and this is why, but sometimes you're just like, which way does it shift? And you want to be able to do it fast. So you guys are going to do some quick fire practice. Woo! Okay, that sounded really exciting, and I don't know that it's that exciting, but we're going to try it anyway. What you're going to do is you are going to decide, say for example, in this reaction, the direction of the shift, that goes in our first column. So if we increase N2, that's going to shift to the right. And if we shift to the right, that means that our concentration of N2 will be going down. Concentration of H2 will be going down, and concentration of NH3 will be going up. Okay, if we decrease the H2, that's going to shift it to the left. N2 is going to go up, H2 is going to go up, and NH3 is going to go down. So we have a whole bunch of these. So see how good you get at doing them. Okay, start at whatever pace you think you can manage, and then just see if you can pick up the pace over time. Okay, and there's page 62, 63, 64, and 65, and 66. Okay, so lots. 62 to 66.
And I would do the
You're not meant to do that, like. You're meant to do
Yeah.
that.
Where did you say that?
I don't know how to do it.
Like what is getting produced the NHP more the reaction from because NH3 increases that they're trying to bring NH3 back down. I think that's how it works.
Yes. But that's what we're doing, right? Yeah. What's messing it up? I don't know. Okay, right. Okay. Well, let's look.
Down, yeah. I know it is. Ron, you're the same one. Yo.
And it turned out it was hard. So I just turned it into reverse.
Yes, yeah, exactly. Bro, like then it was like,
I know, right?
you know, stop these.
Oh, I see. Yeah. That's why. You're welcome. Great.
Oh.
Yeah.
Oh, bro, actually, you know, it's just like, actually, this is like, yeah.
Okay.
Yeah.
I don't. Okay, so what I do is I move it start small.
How was the first one? How was that? Like, was it here, like, I'm confusing. Because how did it go to this or you?
Yes. So draw a little picture. Same.
Yeah, so this is two.
Yeah.
This is one part. Which I think.
Yeah.
If you're doing sun, especially when it comes out right on.
Yeah, yeah.
Yeah, oh, okay.
That is crazy.
Okay, so.
You might not do that, but you do at least then. You're done. Their dogs drop. I'm stuck at those over there.
You guys got it.
I believe. And my coach still instead of the lineup. That needs what I'm gonna be playing with, so I can like communicate, please go back to or else I would get my. pressure is no, this one's left. The volume increases, it wants to go back to, it wants to increase, it wants to go to things for more gas form. This one has 4, this one has 2. Oh wait, this the What? For H2 is equal. I wonder how long we're gonna do this. Like here, it should also be increased. And this is just or I don't know, maybe go down a lot. So we oh shit, I am right here. Yeah.
How are you guys doing? It's what?
It's weird stuff.
It's weird stuff, but is it easy?
And
This is Monday. Monday. Okay. People have lots of time.
Some people even have Sunday story.
Yeah.
So this part of the, I mean, it is.
Yeah.
First day. And it's almost having a
Yeah.
everything is. No.
This song literally feels like Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. That's
It's more of like, okay,
Yeah.
makes sense to have like a
started Monday.
Yeah.
Day.
but like not everything's about working.
Wait, this Ben,
Sorry. You all. Hello.
I don't know what temperature, if it's increasing temperature, which way is the left or right?
Okay, so treat temperature just like treat NH3. So if I increase NH3, it shifts to that.
Oh.
And if I increase temperature, it shifts to that. Does that make sense? Yeah.
I would like to who's a period to do this stuff.
Oh, okay, so what you're gonna do is you're gonna say it goes left. It is this way, yes. So this is gonna get smaller because you're using it up. These are gonna get bigger because you are increasing them. Yes. Okay. Cool. I saw another hand. There we go.
What?
H2 is D.
Oh.
It's gonna go right. It's gonna go down. The N2.
Oh, I just so much. We're not.
Right.
Like it will end up higher than it was before, but the shift will go down. Does that make sense? So it's going to go up and then it'll go down and then it will get higher than it was. It ends up higher. Is it down? Because the shift, yes. But you're correctly and up higher than it. Yes.
It's right here.
Okay, so for those ones,
What the heck? It'll just be in there.
Oh, look, yeah, the two rates are equal enough, the concentration to not change. And here, they're really made of. You have to say like, so they not change. Definitely that will say that they are, but they are constant. So I would have to say, we have to change long term arrow to like, still stay. Right, so now it's just kind of. So it does not shift, it does not shift, right? That's against the
Yeah, that's right.
Oh. That's not in there. Oh, we're missing the side yeah. Oh. Well, that's it. I'm in the code chemistry. Yeah. Yeah. The favorite way.
I'm going to throw on 67 and 68 as well. 62 to 68.
Why?
Why?
Not why. It's like not why. It's like oh my god. It's like oh.
It's a lot.
Yeah.
Gotcha.
This statement is actually. So many layers. Let's go Jimmy. I think skip it up. Yeah. If I this man is about I'm super I think it or just be like, okay. Yeah. Think about it because like concentration shift you get this from like this and my cat as well. All right. You can just do that. Right. Nice, yes, yes. Didn't I didn't drop. Yeah, because they I think once like this game was not like I look at actually what this game was before. His family drives. So like why do I just but it's I think it's definitely number one. Number two, oh, the I can see how I be able to. Yes, yourself. You are a great brand. Yeah. You know what that magic. Yes. You make my brain. Who ended up oh. Yeah, but I think I should go back to town. I just think yo, we did the wrong thing. I think that's the right guy. Yeah, great diagram. That was
This is right.
really? No, so like this like looks like
Oh.
a diagram. Yeah,
Yeah.
and I was thinking that's actually just a random diagram. Yeah.
There should be a spike.
Yes.
There's no spike. Would you like some oil?
Yes. That would be lovely.
Okay. Perhaps with a pencil. Or erasable pen. Would you like to borrow an erasable pen?
Yes. That's the one.
I don't know if this one is.
It's,
Okay, I'm making a mess. You can do that.
yeah. Thank you so much.
This balance.
Yes.
What's the overall? How do you write the overall?
Overall change means like, you know, when you have like a spike and then it goes down again, but it never quite makes it to the original. So it goes up and then it goes down, but it ends up higher than before. The overall change would be up because it goes up more than it goes down.
How do you write that? Like,
The overall change would be, describe the change in the concentration of CO2. So if CO2 is added, the concentration of CO2 is going to go up. It's going to come down, but it ends up higher than before. So overall, there's an increase in CO2. Yeah.
It has actually finished. Died.
Oh, did it just die? Okay.
I'm
not.
You can wash. It's time to replace the source. The heat source of there.
There you go.
Thanks.
No worries. Good. Yeah.
Yeah, that's fine.
Okay, so here, what I always want to do when you're speaking about pressure, draw yourself a box of it. Increases.
Yeah.
So we want our molecule space to more. So we're gonna shift this direction. Yeah. Yes. So, and then if you're going, if you're making it smaller, and you have less room, less stuff. Now this one over here has the same number of gas bubbles. So no shift. Yeah. Yeah. That's what's important. Yeah. Yes. Okay, so we added two.
It's not good. Yeah, but still, can we? Yeah, I'm up. Yeah, still. And let's take a look at the diagram. So this is 24. Hold on. Right? Well, that's sure. Right?
Good. You sounded sure.
Just take a little bit forward. Yeah.
Yeah, it works.
No, because no different. Yes, yes. We already know. Oh, those in the button. Here, this is like almost so. Yeah. Let's take a look. It started recently. So I didn't really see that like those numbers are. We don't know. Yeah. They just pulled out like, you know. Not sure. It's okay when I say oh, fine. I know. Great. This is not like that. Yeah, I wonder that. Grandparents are really good at physics. Anyone? Looks strong. No. Tara. Oh, good. Or
Yes, you are. It's not.
I could probably manage my way to 11. Physics 12, it would require like I
Yeah, thank you.
You're welcome.
Yeah. It is. Both.
Yes. Yeah.
Yeah, if forward active, they're not gonna then reverse that. Yeah, so the.
Yeah.
Oh. I would draw. I didn't know. What is two? Oh, very close. But isn't that just yes? So it literally still wins. It literally still wins. Oh, rice is the reaction. Rice is the rice is the reaction. Ice is the Cajun boulder for older. And then what is Christ? Bro, you know what? Somewhere around. Yeah. Right. Yeah. Bro, for the right. Yeah, you know, right. Oh, I thought it. It's gonna be tough today.
Yes.
I can't wait to do right.
Can I reach the last part?
Well, you can either do it yourself or you can use my book and just like, you know, whatever. What would you prefer? Do you want to do your own notes or do you want to do my notes?
I'll do because I'll put it for me. Because it'll be easier to explain the concepts.
Yes. So. For
And when would
rice,
that be, like, according to your timetable?
let's see where we're at right now.
I didn't see you.
So I feel like. Why would you at this point these are.
Oh, if you actually look at it,
No?
You know what? I will practice for enthalpy.
Okay. Yeah, sure.
Then like
Yeah. Okay.
What's on Thursday? Then probably be.
So tomorrow's my good Friday.
No, it's more like I would have practice.
Yes.
What?
It's a chair. You wanna try it?
How do you like sit up?
You kneel. Yes. It's good for your back.
Yeah, because your back's straight. You're still sitting.
Yes.
But how do you teach that then? Only your head's.
Oh, I just use it for like sometimes if I'm sitting and I'm like, oh, I should really like not sit in my regular. Yeah.
So I think that most of these first two units at least, I feel like the first 3 units is basically like the blocks for units.
They really are. So
I know the most help I would be in would be the last one.
Understanding about.
electrochem?
Yeah, because I know exactly where everybody is. Because that's where I messed up.
So true. So true.
You told me not to do that, and I still
And you did it. I know. I know. Stop recording.